Good morning, everybody. Nice to see you guys here. Nice to see you guys here this morning. We are going to go ahead and get started talking about, today we're going to be talking about the ideal gas law, but before that we're going to go ahead and go over last time's work. We were talking about Charles' law and absolute zero. So just say hi to me. I see N is here. Anybody else? And so a couple things. Let's see, a couple things that I do want to mention. So first of all, I think there's a diversity concert or something tonight, so make sure you guys check that out. That should be cool. And secondly, I'm planning on having, I think we can have maybe a quiz on Monday just to see where everybody's at and all that kind of stuff. So a quiz on the stuff that we've done so far, not at all on the new stuff that we're going to be talking about today, but just a little quiz just to see where everybody's at and all that kind of stuff. Okay? All right, so hi everybody. Let's go ahead and get started. I believe I solved one of these things last time, number 4. I think I solved that one. So we can go ahead and we can skip that one, but we're going to go ahead and go through the other problems here together about Charles' law, absolute zero, these different temperature conversions, and all that kind of stuff. So let's see. Let's get started. All right, so Charles' law, we have that. Charles' law, there's a couple different ways that we could write down the equation for Charles' law. I suppose the simplest way would be to say, let's say that volume over temperature is a constant, or you could write V1 over T1 equals V2 over T2, or you could flip them. Okay, and the thing that we need to remember about the temperature is it must always be in Kelvin. Okay, that temperature, no matter what, it's always in Kelvin. Okay, so we've talked about absolute zero. We've talked about the meaning of absolute zero. The meaning of absolute zero basically is that all atomic motion stops. Right, at absolute zero, all atomic motion stops. It's 0 Kelvin or negative 273 Celsius. So we can go ahead and convert these temperatures into Kelvin. If you're going from Celsius, you're always going to be adding 273, right? So Celsius, so 10 degrees Celsius is going to be 283 Kelvin. Negative 75, so that's going to be, again, adding 273. So if we're at negative 75 plus 273, it's going to be 198 Kelvin. And notice, again, there's a degree symbol for Celsius, there's a degree symbol for Fahrenheit, but there's no degree symbol for Kelvin. It's always just K for Kelvin. Okay? For Fahrenheit, you have to do a couple different steps there to get from Fahrenheit to Kelvin. You have to go from Fahrenheit to Celsius first before you can go to Kelvin. So let's do that. If you're going from Fahrenheit to Celsius, you're going to use this equation right here, where you take 45, so that's 45 degrees Fahrenheit, subtract 32, and then divide by 1.8. Okay, so 45 degrees Fahrenheit is 7.2 degrees Celsius, and we can go ahead and add 273 to that, and you're going to get 280. 280.2 Kelvin. Okay. All right. So moving right along, number 4, I believe we solved that last time in class. So if you're unsure about that, just go back and check the previous day's homework or the previous day's live stream. And I think this is the last thing that we did that day. So let's just jump down to number 5. We have 1 liter of gas. And this, we can just identify these things as we read through the problem to make sure that you're understanding what this is. So 1 liter of gas, and we can look that it's undergoing some sort of change. So this is going to be our V1. This is going to be our T1. This is a temperature. But of course, we can't use 100 degrees Celsius. We must always convert to Kelvin. So that's 100 degrees plus 273, or 373 Kelvin. And is heated to 300 degrees. This is our T2. So that's 300 plus 273. So that's going to be 573 Kelvin. And what's the new volume? So we want to know, okay, what is V2 equal to? Okay, so same kind of equations that we have up here for Charles's law. And we can go ahead and write that out. I'm going to choose this form of the equation simply because V2 is in the top. It's a little bit easier to use that way. And if you ever want one form that's going to be useful for any kind of thing, you can actually cross multiply and you'll get this form. So V1 over T1 equals V2 over T2. If you cross multiply, you'll get V1 T2 equals V2 T1. And this form probably would be the easiest to reach any different kind of equation that you want to get from Charles' law. All right. Or you could just start from here or start from the other form of this equation. They're all mathematically identical. So if you have T1 over V1 equals T2 over V2, this is fine, that's fine. They're all mathematically identical, and you can verify that yourself using cross multiplication and see, okay, you'll get the same exact thing right there. Okay, so jumping down to number 5, I'm just going to say, all right, so if I'm solving for V2, I have got V1 over T1 equals V2 over T2. If I want V2 all by itself, I'm going to multiply both sides of the equation by T2 to get rid of this. So that's going to get me, so let me just do that right here. So if I have T2 here and I have T2 here, multiplying both sides by T2, this T2 over T2 is going to cancel out, and we're going to be left with V2 equals V1 T2 over T1. Plug in the numbers, and that's going to get us 1 liter, that's V1, times a T2 of 573, making sure that we always use the temperature in Kelvin, times T1, which is 373. And let's get that. So that's just going to be 1 times anything is the thing itself. So that's going to get us 573 divided by 373, which is 1.5. We have, only 2 significant figures, so just 1.5 is going to be our final answer, 1.5. And what should the units be? Well, we notice that Kelvin over Kelvin cancel out, and we should be left with just liters. So it's 1.5 liters, and we're solving for volume, so that makes sense that liters is going to be our units for volume. Okay? All right, so if you guys have any questions, just stop me. Feel free to ask me questions in the comment section. I'm going to go ahead and just bring this a little bit closer here. And let's continue on number 6. Right, 343 milliliters. That is a volume. So this is going to be our V1. 25 degrees Celsius, that's a temperature. So this is going to be T1. And we'll go ahead and convert that to Kelvin by adding 273, which is going to be 298 Kelvin. It's cooled down, so we are expecting a decrease in temperature, right? And it's cooled down until the volume is 150. So this is going to be our V2. What's the new temperature? So we're solving for T2. Okay? So you can use whatever appropriate form of the equation that's going to get you to the rearranged equation the easiest. I'm going to go ahead and use V1 over, I'm going to use T1 over V1 equals T2 over V2. Multiply both sides of the equation by V2. That's going to get me T2 equals V2 T1 over V1. Okay? Just multiply both sides by V2, gets me V2 over here. And so here's my rearranged form, and then I plug in the numbers. It's very easy to flip this V1, V2, so that's the thing you have to be the most careful about when you're doing that. Just be really, really careful that you're getting this math correct. So V2 is 150 milliliters. Our T1 is, what is that? That's 298 Kelvin. And our V1 is 345 milliliters. Milliliters are fine to use as units as long as these two units are the same, which they are. So we're good for units there. Occasionally you have to convert units to something more appropriate, but this time we're fine. So this is going to be 150 times 298 divided by 345. And that's going to give me 129.56. I think, let me see, we have really only two or three significant figures, depending on how you look at this 150 right here. But I'm going to go ahead and just round that up to 130 because we have a 0.5 here, so it should round up. So we're going to just round that up to 130 Kelvin. And if you want to, you can subtract 273 and convert it into Celsius. If you want, that's going to be negative 143 Celsius. But you can just leave it as Kelvin if you want. So 130 Kelvin is your answer. Okay, or if you got negative 143 degrees Celsius, that's also correct. Okay, and if you have some, decimal points or something, that's fine too. It's just we are limited in terms of significant figures here and here, so shouldn't have any more than 3 significant figures. Although you do have 2 significant figures here in the temperature, when you convert it into Kelvin, it does turn into 3 significant figures. So we can round it to the nearest whole number for your temperature, 130 Kelvin. All right, so not seeing any questions. How many people we got? We got 6 people. All right, so hi everybody. I see 3 of them here. And if you guys, again, have any questions, just stop me. We only got 3 more problems, so let's just finish this up then. All right, number 7. To what temperature do you need to heat a gas at what's poppin'? Yeah, I don't know. To what temperature do you need to heat a gas at 0 degrees Celsius if you want to triple the volume? Now, here's a somewhat different kind of question. Why is this different? Because we don't know what the initial volume is, right? All you know is that we're going to triple the volume. And there's 2 different ways you can solve this. You could think through this in terms of what makes sense, or you could solve it mathematically. And I want to do both of them for you. Let's think through it first, okay? If we're going to triple the volume, and let's think through what does that mean in terms of the whole Charles' law. Well, Charles says that as the volume goes up, the temperature goes up. Or actually, he said it the other way around. He said as the temperature goes up, the volume goes up. But if we want to triple the volume, right, if the volume is going to be 3x, right, 3 times whatever the initial volume is, the temperature should also be tripled. Okay, so if we're going to triple the temperature, well, what do we do to this? 0 degrees, well, 0 times 3 is just 0. If you realize what mistake I just made, you're awesome. Okay, 0 is in degrees Celsius. This should be in Kelvin. So this is going to be 273 Kelvin, and we want to just triple it. So you're going to triple it by doing 273 times 3, and that's it, 819. So your final temperature is going to be 819 Kelvin. Now, if you want, you can go ahead and convert that back to Celsius. There's no need to do that, but just in case, let's go ahead and do that. So subtract 273, and this is going to be 546. And interestingly enough, so 546 degrees Celsius. Interestingly enough, that 546 is simply going to be 273 times 2. Notice that, right? Because we've essentially added 273 multiplied by 2 and then subtracted 273. So it's really just 273 times 2. But that's just, that's beside the point. That's not that important. Okay? So notice all we've done is just triple the temperature and made sure the temperature was in Kelvin. Every year, in every single one of my classes, somebody always forgets to convert to Kelvin. Don't let that be you. Every single problem for gases, always convert to Kelvin. Okay? So if you don't, it will definitely be wrong. The temperature must be in Kelvin. Otherwise, you can't do any of these Charles' law or ideal gas law, which we're going to do today. must always be in Kelvin. Now, the other way we could do this, if you didn't think through this, if this was something that eluded you and you just wanted to know how can I fit this in the formula? How can I use Charles' law? The other way is just to say, okay, if we're going to triple the volume, we want to figure out what is V1. We can just assume, we can just assign it to something. Say, okay, V1 equals 1 liter. If I'm going to triple the volume, V2 equals 3 liters. And you're good. All right. And then, of course, your T1 is going to be 273 Kelvin. And then you can go ahead and solve for T2. The same way you would do for any of these other Charles' law problems. Right. So notice what we've done. And this works universally anytime you have any sort of problem where something is doubling, tripling, and you don't know the initial or the final. You can just say, well, I'm going to assume this is 1 liter and the final is going to be 3 liters. You can assume this is 10 liters and 30 liters. Anything works because it doesn't tell you, and so you know, therefore, that anything will work. It doesn't matter what the initial volume is. You just make it to be the easiest thing possible for you, and that would be 1 liter. Okay, and so then you can go ahead and plug this in and you'll find that the answer will work out to be exactly the same thing, right? You'd say, okay, well, that's going to be T2 equals V2 T1 over V1, where V2 is 3, V1 is 1, so the denominator now is just 1, and this is going to be 3 times T1, 273, to get 819, and that works, okay? But you'll find it to be easier if you can reason it out, and that's going to be a faster way to get to the right answer. But this works too. All right. 2.68 gallons of a gas at 23 degrees Celsius, heated to 225 degrees Celsius. What is the new volume? Let's go ahead and go through that. And the gallons is a volume measurement. All right, so this is going to be V1. This is our T1 at 23 degrees Celsius, right around room temperature. So that's going to be 296 Kelvin, right? And it's heated up to 225. So this is our T2. Let me go ahead and just do that in my calculator. 273 plus 225 is 498 Kelvin. And we are solving for what is the new volume. That's what we want to figure out, okay? So you can use the same equation that you rearranged before to solve for V2. That's going to be V1 T2 over T1. And in general, you're going to find that these are going to be your rearranged forms of the equation for Charles' law, either solving for T2 or V2, because you never need to solve for V1 or T1. Because if you need to solve for V1 or T1, you could just change what's 1 and what's 2, or rearrange for those. It really doesn't matter. But your V2 is going to be V1, and so that's going to be 2.68 gallons. And your T2 is 498 Kelvin, all over 296 Kelvin. Kelvin over Kelvin cancel to get you gallons as our units for answer. 2.68 times 498 divided by 296. And that gets us 4.5. I think we actually do have 3 significant figures because, of course, when you convert these to Kelvin, they have 3 and 3. And so that should be 4.51. I know that 0, we just want to just drop it off at 4.5, but it should be 4.51 for 3 sig figs for this one. 4.51, and the units are gallons. All right. So no questions so far. Still got only 6 people. Everybody else sleeping, going to watch this later, hopefully. And the thing about this is, hopefully you guys are, well, I don't even need to tell you guys because you guys are actually here and actually paying attention. But everybody else should make sure they're following along and doing this stuff and making sure they learn in it, because when the test comes, you know, nobody's there to help you out and you don't have unlimited time, right? It gets, if you don't know the stuff, it gets tough if you have a limited amount of time to do this stuff in. All right. 835 milliliters of a gas at 69 degrees Fahrenheit. Look at this. We have a mess of different units, right? And then we have this liters. Okay, so when you get a problem like this, so let's just identify everything first. This is going to be our V1, right? And 69 degrees Fahrenheit, this is going to be your T1. So you're heating it, so you're expecting a higher temperature. And this is going to be our V2, and we're solving for T2. Now, notice here that this is significantly more, this is milliliters, and this is liters. So we need to make sure these two are the same. Now you can do that however you want. You can either divide this by 1,000 or multiply this by 1,000 to get them to be the same. It doesn't matter as long as they are the same. I'm going to go ahead and divide this by 1,000. So this is going to be 0.835 liters, right? So I just take that decimal point, move it 1, 2, 3 spots to the left, and we're good. That's our value for V1. Or you could convert this to milliliters, make that 1,440 milliliters. That would be good for V2. Okay, but you don't want to convert them both. They just need to be the same units, all right, which they are. But temperature must always be in Kelvin. So we're going to go 69, convert it to Celsius, then convert it to Kelvin. So if you don't remember, the way we're going to do that is 69 minus 32, right? Because 32 degrees Fahrenheit is 0 degrees Celsius. So minus 32. And then we're going to divide by 1.8. And that is 20.6 degrees Celsius, which makes sense. That's, you know, like a kind of what the highs have been here recently, around 69 degrees Fahrenheit. Now we're going to add 273, and that's going to be 293.6. 293.6 Kelvin. Okay, and I'm going to make sure I just leave this number in my calculator. You don't want to use, for example, 294 or something like that in the calculations. You don't want to round till the very, very end, right? But all right, I think we're ready to actually plug these in now. So we want to solve for T2, and we're just going to use the same equation that we have up here. No need to do our rearranging again and again and again. We already have an equation of T2 equals V2 T1 over V1, which is going to be 1.44 liters times our T1 of this 293.6 Kelvin all over this 0.835 liters. Super important that you recognize at this point why it's important to write down your units, okay? If you just really quickly gone through this problem, you very easily could have put down here at the bottom 835, and if you didn't write down your units here, you wouldn't realize that your units don't cancel out. So it's another reason why we want to write down our units in the calculation itself so that you see, okay, liters over liters cancel, and now my answer is going to be in Kelvin. Very, very important. Write your units down in your calculation itself. Make sure that you have the correct units, okay? So let's take this temperature times 1.44 divided by 0.835, and that's my answer. Not my final answer though, but it's my answer of the temperature at 506 Kelvin. 506 Kelvin. Why is it not my final answer? Because the question asked me, it's very important to actually read the question to see what it's asking. What is the temperature in degrees Fahrenheit? So we need to convert this back. Sorry, I know that's so annoying, but let's go ahead and do it. So we're going to take this number, subtract 273, convert it first to Celsius. So that's now your temperature in Celsius. And then what are we going to do? We're going to, let me see, we're going to multiply that by 1.8 and add 32 to get us 400 and, let's just round it off to 452. I think that's reasonable, yeah. So we're at, yeah, that should be 452 degrees Fahrenheit. Okay? And here it's interesting that Fahrenheit and Kelvin are fairly similar. I think that, yeah, that does happen around these temperatures. So that is it for your homework. Any questions on this at all? What's going on with everybody? How's it going? All right. Feels like we've been doing this for a while, because we have been doing this for a while. It gets kind of annoying after a while. Sorry, guys. It's almost summertime. Hopefully summer is going to be a nice time, but we don't know what's going to happen this summer. I don't know. I have been trying to find some sort of suppliers that can sell me some good masks that I can use and distribute and sell myself, but it's been very, very difficult and challenging. I wouldn't be surprised if they would come up with some like mandatory mask wearing law here in America, but who knows? We'll see what happens. All right. So with that said, let's see. Okay, great. So Luke, so you're good now? Any questions before we get into new stuff? All right, so if there are no more questions, we're going to jump into new stuff. All right, cool. Here we go. We have ideal gas law, which we are covering less than the honors class covered, because we do want to continue on and get through everything. We definitely want to get to nuclear this year and go through nuclear, which is pretty cool. And you guys are going to be doing a little bit of research in nuclear and figuring out different stuff about nuclear power plants, and we're going to learn about nuclear bombs and all that stuff. It's going to be pretty cool. But we need to get through gases first. So we're not covering completely everything, let's say, that the honors class covered, and we don't need to. We're all good. All right. So for the ideal gas law, and before we even start working on these, let me see. I did see anything to print for the new worksheet. You didn't? Really? Okay. I put the new worksheet up in Google Classroom. At least I thought I did. I'll go check to make sure I did that. Maybe I forgot to save it or something like that. But I thought I put the new worksheet up in Google Classroom, and I will make sure to go check to make sure I did, because maybe I didn't. Maybe I forgot to upload it or forgot to save or hit some button, and I'll go make sure it's up there, okay? So ideal gas law is going to be homework 10.4, and so you got it. Okay. So if Luke got it, then it's got to be there somewhere. And if you have problems with it, just email me and I can email it to you or something like that. Otherwise, it should be there. Okay. So reading your book about the ideal gas law, first I want to mention a little bit about Avogadro's law. We're not going to solve any Avogadro's law equations per se, but I just want to mention it real quick. Okay. So just kind of to think about the whole gas laws and gases in general, you have this whole thing where there's different properties of gas that can affect other properties, okay? So if we ask ourselves, okay, what does the volume depend on? So far, we have learned that it depends on the pressure, right? And we've said as the pressure goes up, then the volume goes down, right? So if you compress a gas, so if you push down on a gas, it will compress and the volume will decrease, right? That's Boyle's law. And we've also said, what about temperature? As the temperature goes up, as you increase the temperature, the volume also is going to go up, all right? And that's Charles' law. As the temperature goes up, the volume goes up. As the temperature goes down, the volume goes down. So these are directly proportional. These are inversely proportional. And we can look at them in terms of what they look like mathematically, where you have PV equals a constant, or you have your V over T equals a constant. Now there's one more thing, one more main thing that the volume of gas depends on, and that is the amount of gas, kind of the most obvious one of all. If you want to increase or inflate the volume of a ball, you pump more gas into it. Same thing with your tires. You're going to pump more gas into it. And so we represent, and you might be wondering, well, what is kind of that main thing that the amount of gas really depends on. Is the mass of the gas or is the number of particles? And the answer is it's got to do with the number of particles of gas, not the mass of the gas. So it doesn't matter how much the gas weighs. What matters is the number of particles, which we're going to represent using N. And we recall that N stands for moles. Okay? So the moles of gas, as the moles of gas increases, we would definitely expect the volume to increase, which is exactly what happens. As you add more gas, the volume is going to increase. If some gas leaks out, the volume is going to decrease. Or if the volume doesn't change, the pressure is going to change. And so those are all kind of interrelated. Okay? So as you add more gas, the volume increases. As you blow up a balloon, the volume of the balloon increases. If you have a leak in the balloon and your N goes down, the volume goes down. So these two are related. And so we could also say that the volume over N is going to be a constant. Okay? So this is known as Avogadro's law, or we could state Avogadro's law in another interesting way, and that is this. If two things, two balloons, two containers, two whatever, if two or more things of gas have the same volume, they also have the same number of gas particles. Right? And we're going to represent that using N, or number of moles, gas particles. All right? No matter what the type of gas. Okay, so what do I mean by that? I mean that if I have a mole of hydrogen, a mole of oxygen, and a mole of nitrogen, they all have exactly the same volume. Of course, it's going to depend on temperature and pressure. As long as their temperature and pressure are the same, their volume is going to be the same, as long as they have the same number of moles. So if two things, or three things, or four things of gas have the same volume, they're also going to have the same number of gas particles, no matter what type of gas it is. So it doesn't matter. It doesn't matter what kind of gas you have. It doesn't matter whether it's oxygen or carbon dioxide or radon, for that matter. They're all going to have exactly the same volume when they have the same number of gas particles. And that's what Avogadro's law states. So this is Avogadro's law. And if you recall, we talked briefly about the scientist Avogadro when we talked about moles before. So Avogadro, he's kind of the guy that did a whole lot of stuff with moles. Okay? So that's Avogadro's law. Now, what we're going to do today, because we're not going to really solve any problems with Avogadro's law, which is this, which we could, but we're not going to. Instead, what we want to do is we want to combine all three of these different gas laws into one mother of all gas laws, and that's going to be called the ideal gas law. So I'd like to do that right now. Okay? So the ideal gas law basically says we have four different variables, right? Those variables are pressure, their volume, temperature, and number of moles, okay? And so if we know any three of these, we can always calculate the fourth, because these four different variables essentially define each other, right? So as long as you know all four of those, you know exactly, what's going on with the gas. Okay, so they're all interrelated, these four different variables. And if you know three of them, you can always calculate the fourth one. And the equation to do that is this. It's PV equals nRT. And so you might be asking, well, Mr. Ketz, you just threw in a fifth thing. What's going on there? The fifth thing is this R. So you always need to have some kind of constant. This is called the universal gas constant. The universal gas constant. It means where previously we talked about these different constants, and these different constants are not the same, and they depend on your situation. This constant R is universal. It does not depend on your situation. It's always the same. It's always a particular constant. And it has a value of something right here. So R equals 0.08206. And they have units. It has a particular units to it. Liters, atmospheres per mole Kelvin. Okay? Liters, atmospheres per mole Kelvin. And these units here tell you exactly what units your different variables need to be in when you do the calculation. Okay? So let's go ahead and look at a particular calculation that we can do here, and we can talk more about this next time. But let's go ahead and look at a calculation. So we have, let's do a calculation right here, okay? Number 4, all right? So let's go ahead and use the ideal gas law to do this calculation. All right. In number 4, you have 1.5 moles of gas at 100 degrees Celsius, and it has a volume of 12 liters. What is the pressure of the gas? So 1.5 moles, well, this, of course, is going to be your N. And notice that I'm not writing N1 this time, or not writing V1 or T1. Why is that? Because there's no before and after, right? So it says you have this gas, this temperature, this volume. What's the pressure? It doesn't say that anything was changed. It doesn't say that anything was heated or anything at all, right? So this is simply just N. This is your T. This is your V. And you're solving now for the pressure. Before we do anything, we have to make sure our temperature is always in Kelvin, okay? Because the temperature must always be in Kelvin. It needs to be in an absolute temperature. Otherwise, your answer is going to be wrong. So degrees Celsius to Kelvin, we're going to just add 273 to that. So this is going to be 373 Kelvin. And the rest of these are fine. Now, you need to be careful here when you're doing this, and you can look at your units. Let me just even bring this over here. You can look at your units for R. Your units for R tell you that your volume must be in liters, your pressure must be in atmospheres, your moles are in moles, of course, and your temperature must be in Kelvin. So now, unlike previous problems that we saw before, you cannot just use gallons or milliliters as your volume. Your volume must be in liters. Your pressure can't be PSI. It can't be anything else. It must be in atmospheres, okay? So these units for R tell you the units that your different individual numbers must be in. So let's go ahead and solve this. Because this already is in liters, we're good, and it tells us that the pressure will be in atmospheres after we solve this. So we have the equation PV equals nRT. We're solving for pressure. So if we want pressure all by itself, we're going to divide both sides of the equation by V. That gets us pressure is nRT over V. Okay? Let's go ahead and plug in some numbers. N is 1.5 moles. R is 0.08206 liters, atmospheres per mole Kelvin. Now, you can even program this into your calculator, right? Which I believe I have done. So my calculator, if I use R, look, the number's right there. So rather than retyping the number again and again and again, because you're going to be using R, you just, save it in your calculator and you're good to go. Okay? So 0.08206 is R. Our temperature was 373 Kelvin, all divided by 12 liters. Let's go ahead and plug this in. So what I'm going to do is I'm going to take 1.5 times R times 373 divided by 12, and that's going to get me 3.8. And I only have two significant figures because that 1.5 and that 12. So that's going to be 3.8. And what are the units? 3.8. Well, the units are going to be liters over liters cancel, My Kelvin over Kelvin cancels, mole over mole, and my units are going to be atmospheres, okay? You go back to the units of R. The units of R always tells you what particular units your answer should be in. So pressure is going to be 3.8 atm. And that's our final answer there. All right, so that's it for today. Try to work on the rest of this. If you guys get stuck on anything here for the homework, check out the book, or we will go through it on Monday. But I'm thinking that we should have a quiz on Monday. I want to do, so maybe we won't even, maybe we won't even go through this on Monday. We'll just have the quiz on Monday, and then we'll go through this on Tuesday or something like that. So, yeah, I think that's what we should do. And so, guys, quiz on Monday, and I think our quiz is just going to be a simple either Boyle's Law problems or Charles' Law problems, or maybe some kind of pressure conversions or something like that. So we've actually done a fair amount already in this particular unit, and so we're going to have a little quiz on Monday just to see where we're all at, okay? And make sure that we're keeping up with things. So quiz on Monday, be prepared for that, and I think that's it. That's all we're going to do. We're not going to have any new homework on Monday. All right, so see you guys. Have a great rest of your day. Any questions before I just close out here? Wait, can we do number 5, please? Okay, I don't have anything to do right now. I just know your time's up. But if you want to stay here, yeah, I can do number 5. All right, standard temperature and pressure of a gas is defined as 1 atm, 0 degrees Celsius. What is the volume of 1 mole of gas? This is known as the molar volume of an ideal gas. Sure, so we can go ahead and do that one. The volume of 1 mole. So what are we doing this one? This is telling you what standard temperature and pressure is for a gas. And so it's telling you that pressure is going to be 1 atm. And that's defined exactly. So we have infinite amount of sig figs there. And our temperature is going to be 0 degrees Celsius, which is, of course, 273 Kelvin. Make sure you always convert to Kelvin. And the question is, what is the volume of 1 mole of a gas? 1 mole of gas means our N is going to be 1 mole. So we have our equation PV equals nRT. We're solving for the volume, right? And so what we want to do here is divide both sides of the equation by P, and P over P cancels. So that gives us V equals nRT over P. Plug in the numbers. And then now, N is just 1. So that's going to be simple. R is still 0.08206. And your temperature is 273. All over a pressure of, what was our pressure? 1, right? 1 atm. And now the numbers are going to be pretty nice. Really, it's just 1 over 1. The denominator is here 1, so you don't really need to divide by anything. And it's simply going to be we just use whatever you have in your calculator for R, or 0.08206 times 273 times 1, divide by 1, which we don't need to put in the calculator. Hit enter. Ooh, what did I do wrong here? Oh. Put a little decimal point there. 0.08206 times 273 gives us 22.4. 22.4. And the units, of course, for volume are going to be liters, right? We can see the liters right there, and the units for R, but that's it. So 22.4. Okay? So that's number 5. So you guys got the rest to do for homework. And we'll go over this on Tuesday, and we're going to have a quiz on Monday. Any other questions before I sign out? Yeah, no problem. No problem at all. All right. So, see you guys. Have a great rest of your day. Peace.